Welcome back to Decouple and to Krellenstein, episode 2. For those of you who tuned in last week, let's do a brief recap. James came on and recounted to us the illustrious history of the U.S. nuclear build-out and its idiosyncrasies. It was a big learning case for me. Some really exciting and interesting anecdotes, the good, the bad, and the ugly, what went well, what didn't. We kind of wrapped that up with a bull's case for the AP1000, where James was talking about, and this was news to me, that there's a number of sites that are kind of licensed, prepped. You could build an AP1000 on them tomorrow. We might expand on that a little bit. And we also started to look at where things are headed right now, what the path dependencies are. We talked a little bit about the role for SMRs, the rationale behind them, and that having a lot to do with finance. So I want to just kind of pick up right where we left off and dive in. But this episode, we were looking at the past in the previous one, maybe trying to identify some patterns. And, in re-listening to that episode, what I look at and what I understand about plans moving forward or path dependencies moving forward looks like we could be repeating a lot of similar errors. So we titled that episode, what do we title it again? Those are do not learn history or fail to repeat it. Something like that. Anyway, James, welcome back. I'm about to jump on a flight to head out to a conference at MIT in Boston. So my apologies to you and to the listeners for being a little frazzled and unprepared, but wanted to have you back on urgently. Jigar Shah is coming on August 8th. So it's going to be, I think this is going to be an exciting prelude to that interview, talking to the man with some of the purse strings involved. And trying to, in good faith, argue for what we feel makes the most sense, how we can do nuclear well. I've been referring to nuclear recently as it's kind of like an Olympic Games, and like you need your athlete to be absolutely dialed in, on their nutrition, on their sport specific training, on their physiotherapy. Everything needs to be dialed in, because if you show up to the Olympic Games, fat and out of shape, it's just an embarrassment. And so with that glorious analogy in place, I'll hand it over to you in terms of picking up where we left off.
It's funny. You compare it to the Olympic Games. I sometimes compare sort of what's going on with the nuclear industry as sort of, I call it industrial ADHD. It's sort of this idea sort of that we, how do we want to say it? Like, we just did something incredibly hard and incredibly difficult, and it kind of beat our ass a little bit. Excuse my, I don't know if I can use that.
That's kosher.
But it beat our ass, and now we want to do something completely different. Right after the point where it got sort of easy, like a student who just finished a big report and now is distracted by the next shiny object. And the real point that I think we're in the terms of the nuclear sector today is at a really transition point. Today actually was the day that Vogtle 3 entered commercial operation in the United States. The first AP1000 in the US, I think the fifth AP1000 globally that has entered commercial ops. And we talked a lot last episode about this sort of buffet of different reactor designs, different approaches to building nuclear power plants. And then we took that buffet and then we operated it for, a couple decades. And what I like about these evolutionary Generation 3 and Generation 3 Plus designs is what they did is then they took the best of, sort of the hits of that buffet, and then condensed it into a new power plant design that also had some evolutionary improvements, particularly on the safety side. And the safety side, what we'll talk about, I think, which is really interesting, we talk a lot about how it improved safety, actually, and it reduces, if you look at, say, the AP1000 probabilistic risk assessment, it says that it's basically 100-fold less likely to have a core damage event, like a meltdown event, than the existing very, very safe Generation 2 plants that are operating today in the United States. And that's great, obviously, and that's a great selling point. But the real thing that I think really happened here in what we did, particularly on the AP1000 and these passive plants, is actually make the safety systems much simpler and much cheaper to build, at least hypothetically. And that is actually one of the big advantages of passive safety. Yes, it's actually safer, I would argue, and it doesn't depend on external power or even emergency power, and obviously that was a big problem at the Fukushima, incident. But it also dramatically simplifies the systems that are necessary to do that. And we can go a little bit into that. But what I look for, what I'm kind of thinking about, and I'm a small c conservative when it comes to nuclear power plants. And I think this is where Ontario, to you guys' credit, have really gone so well in going in the technology that people are familiar with, that the regulators are familiar with, that the operators are familiar with operating. And that's what, for your guys, it's the can do. And I think for the United States, to be honest with you, it's going to be evolutionary versions of the pressurized water reactor and the boiling water reactor that I think I see in the future, in the near future, really being the major build out. So there's a couple of different avenues we can go on. We can say why I like the AP1000, the licensed sites that are ready to go today if we wanted to build an AP1000 in the United States, and sort of why I like this design so much, and why I think it's sort of, based on the Vogel and Summer experience, kind of gotten a bad rap, even though it's a pretty amazing, and I would even dare say like kind of cool and sexy design.
Well, I think it was, again, probably from a non-recorded part of a previous conversation where you talked about the nuclear industry being champions of finding technical solutions to non-technical problems. And I think some of that is the sort of chasing of even greater safety margins. But the other is this idea that maybe we're off course, maybe, boiling water reactors, pressurized heavy and light water reactors, we're just a step along the way, or maybe even there was a conspiracy, with Rickover, and we should have gone with some other chemistry or technology. You mentioned, I think General Atomics pursued a high temperature gas reactor. Is there a reason? I mean, do you read this in a conspiratorial light, or is there a reason why we don't see breeders and molten salt reactors all over the place? Are they just a harder technology to innovate, or are we ready to just ditch? And I'm playing devil's advocate here a little bit, but ditch sort of what we know to embark on something that's better.
Look, I think there are a lot of applications that we're going to need to have nuclear energy serving, that light water reactors, pressurized water reactor, boiling water reactors, or even your heavy water reactors, CANDUs, are not going to serve. And like process heat applications, for example, are going to be really hard just because a pressurized water reactor or light water reactor operates, gives steam at 300 Celsius, maybe max 315 degrees Celsius. It's just not hot enough for a lot of the process apps. And in that case, for process heat applications, we are going to need new technology. I think looking at where the fuel cycle is going to go, assuming we build out a lot of nuclear power in the future, we're going to need new technology. What I'm talking about is, what can we deploy today? What is the stuff that in the next couple of years is going to be able to deploy commercially and not be research experiments that are ready to go? I am all for us advocating for research in molten salt, in liquid sodium fast reactors, in high temperature gas-cooled reactors. I think we really need to do that. What I'm talking about is, commercially, I am less convinced that those technologies are really ready to deploy now. So just going back to your question, was there a conspiracy? I don't think there was a conspiracy, right, against it. I think there was a couple of coincidences of history that we really started investing a lot of the money in these two technologies, in PWRs and BWRs. But remember, the first real nuclear power plant in the United States, in Arco, Idaho, EBR-1, experimental breeder reactor number 1, was not a pressurized water reactor or light water reactor. It was a liquid sodium, actually I think a sodium potassium eutectic fast reactor, right? And we've seen and as I said, there's been 2 different commercial nuclear power plants in the United States, Peach Bottom Unit number 1 in Pennsylvania and Fort St. Vrain in Colorado, that were high temperature gas reactors. And of course, internationally, we've seen both in France, right? Before France in the 1970s went to the pressurized water reactor, they had their own indigenous gas-cooled reactor technology, as of course did the British. And every nuclear power plant operating today in the United Kingdom, with the exception of one, is an advanced gas reactor. It's a high temperature, graphite moderated gas reactor. Even in the Soviet Union and in Russia, we have a liquid sodium fast breeder reactor program that's commercial, right? At Belarus, where we have 600 megawatts, 800 megawatts, now even a bigger liquid sodium reactor that's going to come online. And what we see just in all of those cases is we don't see them saying we're never going back to light water reactors. In fact, in the British case, we went from the advanced gas reactor, which is the current one, and the Magnox preceding that. Now the British builds are all in the immediate future going to be light water reactors. Same thing with the Russians, excuse me. I'm being a little bit anachronistic there. But the Russian program, right, is heavily on their pressurized water reactor, the VVER, the VVER, not on the BNs, which are their liquid sodium fast breeder reactors. And they've been doing this for decades and decades. So what I'm trying to say is not that these technologies in the future can't play a very, very important role. I just don't think they are as technologically mature as we need it right now in the nuclear sector to be, right? Where I really think what the nuclear power industry needs to demonstrate in the Western world is that we can deliver plants on time, on budget, that then when they operate superbly. And that they're not science experiments, they're boring. Like you don't hear about them because they're just chugging out power 24/7. And what I would like us to see is focus on developing and maturing those other advanced technologies for those applications where we really need them.
Right. So you mentioned a couple examples there. Russia, the VVER, is their workhorse reactor that they've standardized over time, and this is the one that they're printing out locally and is running their export market. China, after sampling the buffet lunch of basically everybody's reactor design, except for they didn't want the Japanese, obviously, because of some underlying tensions there. There's a few reactors they didn't sample, but they got the can-dos, and now they have sort of a side research project. I think they even have a molten salt reactor in operation. They have a high temperature gas reactor in operation. But these are, as you're mentioning, kind of side projects. I'm not sure if Korea is analogous. I mean, they seem to have standardized on the APR 1400. And they are doing some, SMR research and things like that. But they have a workhorse which drives the industry, generates the credibility, generates, the revenue, and then these side research projects. In the States, it seems to be kind of the inverse. You finally standardized a reactor down to the AP1000, and now, I guess you were diagnosing this as kind of sectoral ADHD. We're on to looking at a plethora of other designs. Now, in our last episode, you mentioned, how this all began. A lot of government stewardship with the initial R&D, and then involvement of the private sector in deployment. 3 or 4 different EPCs and technology companies coming out of this. I should say technology companies, probably lots of EPCs. But these were technology companies that did more than just nuclear. They didn't just come into the game with a reactor design. I'm not sure if General Electric at the time was making like washing machines and every domestic appliance you can imagine and everything else. But what strikes me as quite different here, again, with Jennifer Granholm's tweet, which I haven't found, but we'll keep on referencing, is this idea that that's how the Russians and the Chinese do it. Big state involvement, picking a winner. In America, we do things differently. I guess I'm just curious about sort of the psychology, like what is distinct, because this seems to be having a pattern that's repeating itself again in America with this kind of renaissance or a new sort of nuclear age dawning on us. Seems like a lot of the mistakes have not been learned and maybe replicated, but with actors who are much less credible than like 1950s or 1960s General Electric or Westinghouse or.
Yeah. I think as you're alluding to, right, the big 4 nuclear steam supply system vendors that built the U.S. operating fleet, so Babcock and Wilcox, Combustion Engineering, Westinghouse, and General Electric, all 4 of them at the time were power plant manufacturers that made their main product lines, especially when they first started in this, were fossil power plant, equipments. GE, of course, was co-founded by Thomas Edison, right, to make power plant and grid manufacture, grid equipment, and then spurred out, as you're talking about, to electrical appliances. But their bread and butter was building power plants. And the equipment that goes into power plants. Combustion Engineering, as their name implies, was not initially a nuclear power plant company. This was a company that had built a very specific type of a fossil boiler, right? It had huge expertise in steam engineering and building steam thermal power plants. Babcock and Wilcox famously invented a new type of coal boiler in the 19th century and has been going on from the steam age all the way through to the nuclear age. And Westinghouse, right, was George Westinghouse and Nikola Tesla. And yeah, the Westinghouse, they did a lot of work in railroads, but they were a huge industrial company with a massive steam turbine business and were in all sorts of issues. Now, that might have been, just to be frank, that might have been the historical facts that led us to the light water reactors, to these sort of analogous systems that look a lot like a big fossil plant, maybe a lower temperature, less efficient fossil plant. But regardless, there was a huge amount of industrial expertise in building those sorts of thermal power plants that led to that foundation that we got into. But I think to your point, what these companies had, and we can't underestimate this, they had been building coal and gas and oil-fired power plants for decades. And they had the experience of how actually things work in the real world. And there's this great memo by Hyman Rickover from 1952 or 53 about the paper reactor problem. That no matter what happens, every reactor on paper looks better than any reactor that's ever been built. The second you actually try to start building it, you encounter all sorts of real-world challenges that were part of these unknown unknowns. You didn't even know that this was going to be a challenge, and that became a major source of cost drivers, of schedule overruns that just you weren't able to anticipate until you built it and got that operating experience. And that's why I really do think that the industry got it right the first time, right, in the 2000s, in generating these third-generation light water reactors that were based on decades and decades and decades of operational experience that we had in the existing fleet, and also manufacturing and building them. We didn't execute them very well the first time, but now is the best time. I mean, this is why it's so bullish here, is that we got the constructability experience. Let's capitalize on it. Let's not let that go to waste.
So, I mean, it is interesting. There is a plethora of reactor companies now. Many of them which don't look like Combustion Engineering or Westinghouse or GE. Interestingly, the kind of SMRs that are kind of maybe surviving the Hunger Games here. I mean, we're still early. None of them are actually being constructed or deployed yet, but there's plans. GE, Hitachi, Westinghouse. These are companies that again have that credibility of having built large industrial projects, of having a broad array of technologies and product lines of actually doing things. And then we have I'm not sure. I think NuScale is a startup that's completely centered around building reactor design. Oklo similarly, that's a very different model. And a lot of the hype I see around SMRs is, they can plug into smaller grids around the world, but countries that are new to nuclear are unlikely to want to sign a deal with a startup company rather than a state entity like Russia, who's going to take care of all of your fuel cycle needs, as well as financing, building your reactor, et cetera. Like it seems like there's been a lot of naivete in the last 10 or 15 years where, other than Vogtle, the West hasn't been building anything. It's a great time to imagine. But again, the Hunger Games are coming, and we're seeing things getting pared and whittled down. People are all still playing pretty nice, I'm seeing in the discourse. Like no one's yet casting a lot of shade on anybody else's tech, but I wonder if that's coming soon.
So, I think the real question on the grid, I hear a lot of the discussion about SMRs, right? On building a gigawatt scale plant or 2 gigawatt scale plant, if you're talking about a multi-unit large modular reactor. That is, there's a huge grid issue here, right? You can't just pop that down randomly without building a huge amount of transmission infrastructure. But I think for the United States in particular, where we still get a non-trivial portion of our power from coal, and historically, just even 10 years ago, got a lot more from it. There are so many sites in these dozens and dozens of sites in the United States that you would not have to build a single new, foot or meter of transmission lines to just plop in a 1 or 2 gigawatt plant. And when we were talking about what we're talking about in the U.S., let's keep that as an example. Where the Department of Energy is even saying with as aggressive of renewables, wind and solar build out that you can get. Right, we're probably not going to even come close to it. To reach our decarbonization goals, we're going to need probably around 100 to 200 gigawatts of new nuclear capacity. And I'm sorry, there's no way in which we are not going to have to build some new stuff at new sites to do that. But the whole point is there's a lot of low-hanging fruit right now that we could deploy a dozen or 2 dozen new reactors at a site that already has all the transmission there, already has the circulating water infrastructure, or at least access for cooling needs. Let's focus on what the easy stuff is. Let's try to crawl before we run a 10K marathon. And that's what I'd like us to look at. Let's take a design that is built on an evolutionary understanding of 70 years of operating light water reactors and sort of perfected that, took the best of everyone and sort of tried to put it into one design with evolutionary simplification of the safety systems. And that we've built, and we have a regulator that is now, experienced in that regulatory process, and we have a construction and work crews and a supply chain that actually has done it. And more importantly, as we're saying right now, Vogtle 3 is supplying It's at 100% power. It's citing more than a gigawatt of power and powering Georgia houses and homes. And we have 4 reactors in China that have had a remarkable experience of just being super reliable, especially for a first-of-a-kind design in doing that. That is, to your question, if you're thinking about building a new nuclear power plant, one of the advantages the Chinese and the Russians, and to be honest, the Koreans have, is they can say, when Baraka was built, they could take them to an APR 1400 that was operating in South Korea. If you're building a VVER, you can go to an operating VVER. Hualong 1, the sort of standardized 3-loop Chinese pressurized water reactor, there's an operating Hualong 1, right? And you can go and see it. And it's not just vaporware. It's not just a paper reactor. And I would like the West, we should not abandon, by the way, by any stretch of the imagination, developing SMRs. They have really important applications. Generation 4 technology is incredibly important. But that we should be understanding the level of technological maturity that these various technical options are. And right now, we need to prove that the nuclear industry can at least deploy tech on time, on budget, have great operating characteristics once they're done.
So what do you make of plans like, I think it's Lyash of the TVA talking about 20 plus small modular reactors within the Tennessee Valley Authority? I mean, you're getting up. I know you were saying earlier that in terms of, I think your interpretation, the fundamental driver of the SMR logic is utilities afraid of being bankrupted by, large capital projects. I guess this is a potential to sort of feel it out, see how it goes. I mean, how do you envisage those first deployments being? It sounds like this technology is going to be fairly reliable. We're coming off of a long experience with it, but just in terms of the economics, I imagine those first units are not going to be that economical, both some wrinkles to work out in terms of the first of a kind nature of them, first of a kind construction, but also, just them not conforming to economies of scale.
Yeah, so I think, the TVA is focusing on, my understanding for the initial deployment, on the same one that OPG is also, Ontario Power Generation in Ontario is also focusing on, which is the BWRX 300 from General Electric Hitachi. And, I think a lot of us, it's sort of our favorite small modular reactor right now that's ready to deploy, just because the BWRX 300 is it's about as big as you can get as a small modular reactor at 300 megawatts electrical. Right? It is based on a lot of evolutionary technology, although there are some differences there. And the big question that we have to all ask is the BWRX 300 going to be able to compete economically with a large reactor as we start building more of them? And the whole point I want to make here is if you're building 10 gigawatts of new nuclear capacity, well, that's either 10 AP1000s, maybe a little less, or that's going to be 30 BWRX 300s. And that's about as big as you can get. And it's not clear right now if the economics may actually favor the BWRX 300. Let me just be clear. There's a very recently published analysis of this by Karush Shivran's group at MIT that really argued that it's not actually clear. Maybe in some cases where you're labor constrained, the X300 may actually beat the AP1000 economics just because you don't need as big of a workforce at that site. However, I have to say I'm a little bit skeptical that the X300 is really going to be able to compete with the AP1000. If we look at one of the biggest drivers of cost overruns in nuclear plants, it's what we call improvements, the civil works. It's sort of digging down and getting pouring a base mat, getting that rock inspection done, the bedrock inspection done, and really doing that sort of fundamental work of laying a foundation, laying mud mats, and doing that. That's very challenging and very expensive, and doing it to the seismic qualifications that is necessary for a nuclear island is very, very technically complicated. And when I look at the X300, I'm looking at a design that sort of takes that and says, hold my beer, right? It's like saying basically we're going to build for a 300 megawatt plant. We're going to build 150 foot, 50 meter deep a shaft that is 30 feet in diameter, 30 meters in diameter, 90 feet in diameter down, and seismically qualify the entire thing and use we're not sure yet, but maybe use a novel technology called steel bricks to be able to actually line those walls and then build the reactor building and containment within that. And that seems, like a very technically challenging, improvement to be doing, and quite intense. And at the end of it, you're only getting 300 megawatts. When I was at the SMR conference in Atlanta, I was speaking to an old Stone and Webster engineer who had built a bunch of plants. And he was sort of scratching his head at the BWRX 300. And he said, we kind of have looked like we've taken the hardest part of, in some ways, not the hardest part, but one of the hardest parts of building a nuclear power plant. And we've made it, well, not easier. Let's put it that way. And at the end of that process, you're only getting 300 megawatts. So the question that we have to say is, can we really get that process down so much that it actually beats out, say, the AP1000? I'm not so sure I'm convinced.
Yeah, I love this. So and the rationale for going deep like this, is it partially to reduce the amount of concrete needed for containment? Is it a safety measure? I understand it's because of natural circulation. You need a really, really long RPV, reactor pressure vessel. Like what is the rationale? Because I see a lot of, it sounds like a lot of these kind of 3+ designs are requiring pretty major modifications of existing plant architecture in order to accommodate these safety margins, which maybe are nice, but are certainly driving costs and decreasing constructability in my very amateurish outlook. But yeah, specific to the X300, what's the reason for this?
I'm not a GE Hitachi engineer, and I don't mean to speak behind the motivations behind that particular design choice, and I'm not going to. But what I will say is you can guess at a couple things that they're doing. One of the things that has been an issue in getting SMRs really deployed and large reactors is the aircraft impact assessment rule that came into force by the NRC in 2009. And that basically requires, after September 11th, the idea that a nuclear facility needs to be able to demonstrate that it can withstand an impact of a large commercial jetliner intentionally flying into it and still, protect the safety and not have a core damage event occur out of that with high confidence. And this has actually been a major problem with the NuScale design, as you may know, which is this really small, initially this 55 megawatt electrical little power module. And now we had to build it into the world's biggest, most expensive swimming pool. And that swimming pool, the reason why it's the biggest and most expensive is to be able to comply with the aircraft impact assessment rule. And I would imagine that what GEH, and this is not based on any insight, I imagine one of the factors that went into is how do we comply with this rule without getting to very exotic concrete steel, shield building designs, which actually became a problem with the AP1000 with revision 19 of the DCD. So I imagine going underground is pretty nice to withstand a aircraft impact, and I imagine that has a lot to do with it. But I'm not so sure about what was going on in that, and it does. And I've seen, if you talk to GEH, they'll say this is a very, very simple, relatively simple civil engineering process that we do all the time. They're doing, to their immense credit, they are working with a EPC called Black & Veatch, and they're doing a scaled demo of this constructability. I believe it's actually happening at the TVA Clinch River site, and with a lot of government money to do those construction technique demonstration of how we're going to actually build this shaft. But I just want to say, in the thing about simplifying concrete, the AP1000 already takes dramatically less concrete per megawatt electrical than a generation 2 pressurized water reactor or even boiling water reactor. And same thing with, just simplification of the system. I mean, just to go back to the AP1000, right, we have 50% fewer safety grade valves in the AP1000s compared to a Gen 2. We have 35% fewer pumps. We have 80% less safety grade piping. We have 45% less seismic building volume and 70% less cable in the AP1000. And despite that, we didn't just hit the AP1000 out of the park. It kind of shows this sort of the paper reactor issue that when we have all that simplification, that is great. And that really can, in the long run, be able to get us to a much more deployable, constructible design. But it doesn't guarantee it. And if you don't get the basics correct, no matter how simplified your design is, you're not going to be able to just deploy these power plants sort of willy-nilly and turn a key and get them built. It's a lot of this is the practicality.
Well, as I understand it, it's a pretty fascinating history because the AP1000 was originally the AP600, and the way to justify cranking out a reactor with a smaller economy of scale was that it was so modular, it would snap together, we'd get construction done in like 2.5, maybe 3 years. I think I remember seeing some promotional material like that. I mean, it's an extraordinary history, and now we're getting into the AP300. It's just, we can't make our minds up about what kind of numbers to put after the letters.
Once again, I think the AP1000 also is actually not that much larger than the AP600, but it has it's almost double in size. in terms of power generation capacity, but the actual physical dimensions of it are not that much larger. But one of the things that I think what's weird about this, the AP600, I think the reason why no one bought it, even though it was design certified, was because it was looked as too tiny. And I think we're kind of going in the opposite direction now, which is interesting. And I do think, to foreshadow something I would like Jigar Shah to talk a lot about, and I think we all can actually agree that probably a large modular reactor, when we're talking about deploying gigawatts and gigawatts and gigawatts of new nuclear, and God hope that's what we get to, a small difference in the actual, price per megawatt hour is going to translate to billions and billions of dollars in difference in the cost. So us figuring out how we can deal with that non-technical problem, which is the project risk, it's the system risk that building a nuclear power plant in the current way we finance new nuclear power plant builds in the United States, how we can deal with that market failure. It's not a technological failure, it's a market failure of figuring out how do we finance these plants in a way that actually utilities will be willing to order them. I think we've spent too much time trying to nuclear engineer that problem, not enough time financially engineering that problem, even though it's primarily a financial engineering problem, because from the nuclear side of view, I really do think that the case is pretty clear for larger reactors for a U.S. type context where we need to deploy those gigawatts.
Well, it's fascinating up here in Canada. The license design we have ready to go is the enhanced CANDU 6, which is about a 750 megawatt reactor. And there's interest in building CANDU. 4,800 of these 6,000 megawatts is designed to be large nuclear, according to the announcements. But apparently the utilities are saying it's not big enough. We want a gigawatt scale CANDU, and it makes you shake your head or do a double take, because at the same time we're using only 1/4 of the licensed capacity of our site that's ready to go at Darlington with 4 BETR X300. So nothing makes sense anymore. It does feel like we're in the midst of a paradigm shift, and there's path dependencies, and some people are set on walking the way they've been walking. But facts on the grounds are sort of changing rapidly.
I think the enhanced CANDU 6 is a really good example of something that is licensed. We have a huge amount of operating experience, and just the way that Canada is hitting it out of the ballpark in terms of the refurbishments and building that supply chain, that industrial workforce really shows. And we've gone a back and forth, Chris, on are CANDUs really the gold standard globally? Well, regardless of your perspective on that, CANDU is the right choice for Canada to do right now. There's no doubt about that. That is the right choice, in my humble opinion, for Canada to do. Because it turns out that whether it's slightly technically inferior or superior, that matters so much less than having those real human, real world factors going on. And that's why I'm saying, I like the AP1000. It's not because it's my favorite, dream light water reactor that I dream about at night, but it is the one that we have a workforce that just built it. We have a supplier that has a warm running supply chain to build that plant. We have a design certification, and now our regulator has gone through the entire regulatory process twice of giving it permission to actually load fuel. Those are such great advantages. Why throw them away? Why are we looking at throwing that huge advantage away? We talk all the time about going down that learning curve. And I agree, we should go down that learning curve. Let's get a jump start. Let's start from the 6th of a kind, not from the 1st of a kind. And that's not to say we shouldn't. I want to be clear. I'm not anti-SMRs in any ways. I'm not anti-Generation 4 technology. But we have to learn from the past and figure out, even if it's not the most shiniest, newest technology, the technology that we can have those very real human factors. Let's create a policy environment and a market environment that's conducive to deploying that technology, and get those and start really actually learning and getting down that. And I just, one of the things that's so interesting to me is that I feel like the AP1000 kind of has been besmirched. But as someone who when I was a kid, I went to one of these conferences with my family, and we saw Westinghouse sort of present on the AP1000. And I sort of heard the very same marketing rhetoric that we hear about SMRs, about these dramatic simplifications in safety systems. It's 100-fold safer than the existing fleet. It's 342, I believe, modules that we're going to snap together on site. We've reduced by over 50% the number of safety critical welds in the primary system. And it turned out that didn't matter as much as having a great supply chain, having a good EPC that was familiar, have a regulator that was well oiled. And what I'm trying to say is, okay, we went through the hardest part. We got to the other side. Let's now kind of take our victory and try to build on that rather than starting from scratch.
Well, I love that that analogy used of the need for maybe less nuclear engineering right now and more financing engineering.
And policy engineering.
Policy
right?
engineering
Maybe is the right way to. Yeah,
absolutely.
Because the nuclear engineering is superb, and if I could just fanboy out a little bit here on the why I sort of love the AP1000 as this sort of evolutionary design that that when I see the AP1000 nuclear steam supply system, I see in that 70 years of perfecting the pressurized water reactor nuclear steam supply system. And what's really cool about this is, as we talked about before, we had three major manufacturers of PWRs in the US, and Westinghouse now is really two of them because they bought the combustion engineering nuclear business, which had originally been sold off to a Swiss company called ABB, but then Westinghouse bought it. So what we did is we kind of took the best of everything, right? If you look at the steam generators in the AP1000, right, they are based on the history of the System 80 steam generators that were first deployed at Palo Verde, and now are, of course, deployed by the South Koreans in the OPR 1000, the APR 1400s. But even going a little bit back before it, they're a little bit smaller than the System 80 steam generators. So they're ones that are really based on the Arkansas Nuclear 1 Unit Number 2 steam generators. Right? The pressurizer is basically the pressurizer that was based at South Texas Project and made bigger, 50% bigger than you would normally see in a classical PWR, so it can better, handle transients in accident situations or loss of feed water transients. The core is built on, Dolph 4 and Tahang 3. I'm probably, butchering the pronunciation of those European reactors. The core shroud is Waterford Unit Number 3. The reactor coolant pumps are based in what our experience actually in the first pressurized water reactors. They're canned like Shippingport and Yankee Row. So we've taken this sort of mixture of Westinghouse heritage, combustion heritage, and we've tried to figure out how can we get the best, what works best, and put it all together into a single nuclear steam supply system. And where we really did that innovation was on the safety systems and making them completely passive, which is just a massive driver of not only safety, but simplification. I don't think we talk about that enough. In the fact that, one of the major drivers of complexity in a Generation 2 active safety system nuclear power plant is just take the emergency core cooling system, right? If you think about what you have, even for BWR or PWR, core ECCS, right? You have high pressure systems like, your high pressure coolant or safety injection, your HIPCs, right? And that requires a whole set of piping, whole set of pumps, whole set of instrumentation and control, and a safety critical wiring and load centers, as well as an emergency diesel generator. And then you have to have a whole low pressure system as well, your LIPSI or low pressure coolant injection or low pressure safety injection, with its own independent set of instrumentation and control, its own wiring, its own independent sets of piping. With passive systems, we're able to eliminate all of that and make some dramatically simpler systems that we have in the AP1000 that don't require external power, that are just eliminate all of that piping and all of that wiring and pumps. That's a huge, huge driver of simplicity. And we've now built it, and we've operated it, and we've licensed it. And that's kind of the best of what I want, right? I want kind of these great nuclear steam supply systems that are economical, that just chunk out power and simplify the safety systems.
So, what's your degree of confidence looking at the past again, maybe at some of the best in terms of Palo Verde, that building a third unit of an AP1000 is going to cost down significantly? Is there an evidentiary basis to that?
It's not just a much smarter guy than me, Kurush Shivran, also at MIT, released a really good report about this, which really showed massive price reductions, over 40 to 50% of what Vogtle costed in the next of a kind AP1000. I'm pretty confident about it. Even if we look at, there were big price reductions from Vogtle 3 to Vogtle 4, right? Just in that one unit. But I think given, as I won't say who, but someone at Westinghouse one time said to me, we did everything at Vogtle about as hard as possible. We just slammed ourselves into concrete walls over and over and over again. And the one advantage that you have of that experience is that we're not going to do it again. And we know exactly how to do it better. And the other thing is that Vogtle was so expensive that we only have really, it's going to be very, very hard to make it more expensive. So we can be assured, I'm highly confident it will be cheaper. The better question I think to ask is, will the industry and will utilities seize this opportunity? You know, if we wait another 15 years or 20 years to build the next AP1000, it might not be cheaper. But right now we have a workforce that's coming off of Vogtle, that's experienced. We have an EPC, arguably one of the best EPCs, Bechtel, that has built this, that has the design. We have a design ready. We have Westinghouse gearing up their supply chain to supply the Polish reactors. Let's take advantage. And we have multiple sites around the country that have gone through the entire NRC licensing process, which is a multi-million-dollar, 5 or 6 year long process. And the NRC is like, we're ready, babe. Like, just make the order and start construction tomorrow. I can't imagine a better situation you could be in where there's zero regulatory risk to start.
What I'm seeing looking around the world is, there's some fine U.S. Reactor designs like the BWX-300. They're not getting built in the States. That's not where the development's happening. I mean, the first AP1000 or first 2 units were built in the States, but now we're going over to Poland to do them.
Well, the first 4 units of the AP1000 were actually built in China.
China, yeah, exactly. So, I mean, there's this tendency now for the U.S. to be developing technologies, but not actually building them at home, trialing them abroad. That seems, is there a historical precedent for that? I mean, there's not a lot of nuclear exporting countries, but it seems odd as an outsider.
Well, remember, I think if you went back just a decade ago, we expected there would be somewhat like a dozen nuclear plants reactors under construction around the country. And that, a couple of historical factors really screwed us, right? We had the Fukushima Daiichi accident in 2011. But even right before that, we saw hydraulic fracturing really dramatically reduce the price of natural gas and increase the abundance of it. So power prices began to plummet. And maybe even a struggle to keep the existing fleet online, as we all know. And then we also were compounded with that. We went forward with Summer and Vogtle, and that was not a great experience. Let's just put it mildly. And I think the problem, if I may be so bold right now, is that the industry, kind of, to borrow a phrase, needs to come out of the closet a little bit about what happened at Vogtle and Summer, and not shy away with it, not hand wave away from it about what the challenges were, but really level with people and say, this is what happened, and this is why it won't happen again. And I think instead, much of what's going on is because there's just a lack of confidence that we're going to be able to learn. We've learned from that. You see a very big reticence of utilities to order these plants. And even the plants that are in preliminary ordering, like the NuScale orders for UAMPS, for the Utah Municipal Utility, we're already seeing massive cost overruns being, budgeted out there. Even before construction begins. So I think we need to get to quote Jigger, we need to deploy right now. And we need to figure out how we're going to deploy and make it an industry-wide effort to deploy. And I personally think the BWX-300's a good SMR candidate to start on that deployment, but we really do need to figure out a way to deploy another large modular reactor, which we know we can build. We know the price can only drop from there.
You know what? I was talking with, I think, Robert Bryce about the not the savior. There's many saviors of Diablo Canyon, but the saving of Diablo Canyon. And, this wasn't a nice to have nuclear reactor. This was a need to have nuclear reactor. California on the verge of blackouts and political careers, presidential ambitions on the line if that had happened. And, this astounding turnaround where the Democratic controlled Senate almost unanimously voted to extend Diablo Canyon. Again, that's a need to have nuclear reactor. What is the driver? What is the urgency to build new nuclear in the States? You've got tons of natural gas. Is this purely, being driven by climate policies at the DOE? Is it, we need to, again, and this maybe is harkening back to the original rationale for building nuclear in the States. We went through that a little bit, that we were using a lot of oil before the OPEC crisis hit, that coal got a bit expensive. What do you see as the actual pragmatic drivers towards building new, small, and even large nuclear in the U.S.? Because words are not enough. Intentions are not enough.
The Biden administration publicly, what they'll say is, we've sort of woke up and tasted reality, right? We look at Germany and we look at France, and we realize that, and even if you look at no matter what, even if you take someone who, historically some nuclear advocates don't think of as very pro-nuclear, like Jesse Jenkins' models, his modeling, no matter which way you look at it, requires firm, clean energy to work, right? In any case, it does not rapidly explode the cost of power in the United States. So from a climate change perspective, we saw that great advanced nuclear liftoff report put together in part by Julie Kozarecki at the Department of Energy, a great person. There's a real, understanding that if we're going to decarbonize, there's going to be a really big role for nuclear. And to be honest, no matter which way, and no matter how many renewables we build out, almost certainly we can't build enough nuclear to help that path. So I really do think for the first time, most Democrats even have come to that realization. And that is a huge, I think, step change that has happened over the last 10 years. And I think we saw it, I think we see it very much in the Biden administration. But on the flip side, we talk about natural gas. And I think there's a huge amount of natural gas still in the United States. But as we saw the Russian sort of energy crisis induced by Europe, I think there's a real now potential for liquefaction, for LNG transport. Historically, we think of natural gas as not a liquid, excuse the pun, market, where it's really dependent on the ability to do pipeline transmission. So we didn't see coupling of the natural gas prices that were happening in Europe with the US. But now with the massive, growth of liquefaction capacity, all of a sudden LNG, natural gas, has become a much more volatile fuel in terms of price, excuse once again the pun, than it has been historically. And if history and economics takes us anything, that market is only going to become more and more of a global market. So I'm sitting here in New York State, where we just shut down an Indian Point 2 and 3 stupidly. And now we are highly, highly dependent on natural gas and oil, actually a lot, to actually power our plant. So I see my power bill jumps up and down per price kilowatt hour based on how natural gas prices go up and down. So we have a major sort of energy security issue, not so much in the ability for us, to keep the lights on maybe, and we're blessed with that, but in the ability to keep our lights on with a dependable price. And what nuclear offers here is it offers this weird bipartisan, issue where is bipartisan support, even if you're the most climate focused, you want nuclear because you need it. And on the right, even if you don't believe climate change is even something we should care about, you recognize the economic imperative of having it to stabilize electric power prices in the U.S. So I think that's why we are in such a place where we saw a recent nuclear fuel bill pass the U.S. Senate with a 96-3 vote in favor of it. And there's nothing really in the United States that we still agree on that, you can't get a post office renamed with that sort of voting record. And so we're in a weird space where for different reasons we can come together on nuclear power.
Right. I mean, this is potentially, reminiscent of Putin's policy of building nuclear in Russia to spare internal use. Don't get high in your own supply of natural gas and free up more for export. Is that kind of what you're seeing as a pragmatic driver beyond climate?
Yeah, I think that the United States is going to try to become a major LNG exporter, especially to Europe, right? And we have the ability to do it. And we've seen massive build out of LNG capacity. We're seeing, obviously, in the European case, the ordering of a huge amount of LNG. And I think, it comes with two sides, as I was just saying. I think, yes, we're going to try to become a massive exporter. And I think there's a real strong economic, environmental, and geostrategic reason, national security reason why the United States should be a source of that. But on the flip side, that comes with making LNG a global commodity that's priced at global prices, that is going to be sensitive on a pricing perspective to global supply disruptions. And something like electric power, I don't think we want to be so tightly correlated to events that we can't control. I just think one of the things that, we don't want to talk about, maybe if you're a very climate-friendly person, but is just a truth. One of the drivers and the reason why I think America pulled ahead of Europe so much in sort of GDP growth is that we had a fracking boom. First under the late Bush, but really through Obama and early Trump, where we increased oil and natural gas production. And I think that was a huge driver of economic growth and opportunity in the United States, especially compared to a place like the European Union, where there's no fracking, basically, that happened. And we see the consequences of that in multiple ways. I think we need to think longer term about how are we going to decouple our global energy markets and the supply that Americans get in their mail every month from the whims of what's happening 5,000 miles away. And there's no better technology, if I may be so bold, than nuclear energy, considering that we have a place like Canada and Australia, and you guys have great uranium supply. And I don't think we're going to be in major conflict with you folks.
The French want some Canadian uranium now too, but
I think a lot of people want Canadian uranium. And I think, the guys at Cameco, to their credit, they are the smartest people in my mind. They bought Westinghouse for a cheap price. They also 49% of it at least. And they have these high grade uranium ore that they have mine sites ready to go. This is a huge win for Canada. And I think a huge win for the United States that Canada is so ready to meet that supply.
James, I'm coming stateside in a couple hours. I'm going to have to cut it here so I can catch my flight down to Boston, going to MIT for a little nuclear workshop. Excited to report on that and maybe interview some folks down there. But a pleasure chatting again. So much more I'd like to touch on and so much more we will touch on going forward, my friend. But thank you for this.
Thanks so much, Chris, for having me. And have a safe travels.